did in fact get another heads on the coin flip, so we have one more quiz. Eventually I'll get a break, and so will you. But here we go. This one's actually going to be a little bit shorter for us. So as a little reminder, the master theorem, this is sort of the conclusion of yesterday and sort of divide and conquer in general. Today's going to be the last day of divide and conquer, by the way. From now on, we're gonna move on to other stuff. So make sure that you understand it now. The master theorem, we found that if we have a recurrence of this form, that is, each call of my algorithm it calls the same algorithm a times on a version of the problem that is smaller, that is n over b for some value b, and each one of those recurrent calls also does n to the c work. This is like our merge step. So we do recursive calls, and then once we do our recursive calls, we combine them, and that requires n to the c work. We found through our whole arguments using the geometric series and all of that, that when we have the condition of a over bc is less than 1, then it's top heavy. The first call matters the most. That is, it is order of n to the c. When it's equal, then every single one of the recurrent layers will be equal, and then we'll have that this is going to be the amount of work done on each one of these levels times the number of levels, which was log b of n. And lastly, we found that if we have that it increases, the amount of work done increases with the recursive depth, then the final layer is the only one that matters. The final recursive depth, that is essentially counting the number of calls to the base case, which is this number right here. Cool? That was the master theorem. As a little bit of practice, you can start the quiz now. We have a little bit less time with the quiz today, so try to get going on it. By the way, for the written response, there's actually one implicit condition that I didn't put on here. F of n has to be monotonically increasing, meaning it's a larger value for larger inputs n. It is a condition that's implicitly you need. Right now? Thank you. Right there. Okay, that's going to be the first phase. I'm also going to give you a little hint on the written part because it seems like not many people have gotten it yet. So the way that we can think about these three cases is this first case. This is sort of the ratio of the growth of the amount of work done at each layer, right? If we recall the whole derivation, this was sort of the factor that each layer's growth. So like each layer did AI n over bi to the c work, if we recall, right? And when we have this value, okay, we can rearrange this if we'd like. If we have that value is less than 1, then it means that as I increases, as we go through the recursive depth, this whole value decreases. So if I drew this as like top down is the amount of recursive depth I have of the number of calls, then we'd say that if the width is the amount of work done, this is top heavy. Right? So we do the most work at the beginning. That's why this is just NC. Because the most work is done at the very beginning. It's just the amount of work done by my initial call. Right? And it diminishes as I go, and I can ignore them asymptotically. This case is when it's exactly equal, where the ratio is 1, so every single layer is the same. This would be like this. So the way that we get this value is we multiply the amount done on each one of these, which would be n to the c, by the number of recursive depth, which is log b. This one, on the other hand, is the reverse, where it is the least work at the initial call and the most at the end. So what we're really doing is we're just counting this last step at the maximum recursive depth, which is really just counting the number of times that we call our base case, which turns out to be exactly this number. Okay? So, for the second part, what we need to find is where each subsequent call is either growing in the amount of work we're doing, or shrinking in the amount of work we're doing, or staying the same. So see if you can find some way to formulate that using the arbitrary function f. There's a pretty nice way to do that. Okay, now you may discuss with partners and work on the last bit of this. Give you another 10 minutes or so based on how much we got done previously.
Which case did you
That's going to be fun. So that puts us in one case.
Yep.
You can't do. I think it would be.
I was thinking one.
Oh no, C is 0.
Oh, right. Yeah.
So wait, I think we got the case wrong. This is actually. This is going to be.
There's actually a very nice way to do it. But it ends up being
Oh, I just
you end up with a
I don't know how to categorize this. Because yeah, we get that it equals it's probably
does the total of the year add up to the same amount per
like it just hasn't like been drawn out.
well, I'm just saying, if I make a square root and make all the square roots, what's the total square taking each data?
So it's probably that last option.
That's the
Square root of that log base square root of that. Oh wait. So then we get log base. Should this be big thing?
That was
I'll go with that. I don't know, it just feels you know what, like just leave 32. I guess we should move on to the what was the C? Do you know? C was 0.
that I wait for the next values are
You have to see a square root of x less than equal to 4 or greater than x minus 2. Once you categorize it as A over B to the C, it's the square root of Yeah, so we're looking at the third case. So now we just have to look at this
All right. I got it up there. I know that a lot of people haven't finished it yet. We have a lot of interesting things to cover today, though, so I don't want to spend too much time on the quiz. The cursed coin made me do the rest of the lectures a little bit faster. Anyway, so for the first problems, all the use of master theorem, it is actually just plug them into this and solve them. It is that simple. That's the main, I'd say the main draw to divide and conquer is the fact that it's very easy to analyze the runtime, and generally it will be better than a naive thing. That's the main benefit of doing something like divide and conquer. We'll see other things that have better guarantees, but divide and conquer is usually good because we can put it in this form, solve it nicely, and usually get a pretty good algorithm out of it. So you can just plug these in. The bonus one is slightly trickier. If you're working on that one, it's sort of an interesting one. For the written response, though, I'm going to actually spend a little bit of time to talk about this. So the hint with this was pointing out the three cases is going to be generally true, is that if we have a function that has some larger terms and then some smaller terms, the larger term is going to dominate. Okay? So in the case of us having one of these, when the largest term of, this is like a summation of all of these layers, when I have a largest term, that term is going to end up being my type bound. So larger terms are going to end up being the biggest term. This isn't always true, like for example, when these are all equal, then we have to multiply by the amount of them there are, and there is some middle ground there where they can be like, you know, n plus n over 2, etc. I'll give me a different term. Whatever the case, we generally want to look at this. And so, if I want to look at conditions for f of n such that this grows as I recursively call it, let's say, then that means that when I call one of these, I want that, like if I do one recursive call of this, right, then the total work of the next recursive layer is going to be a times f of n over b. Does that make sense? So if I look at the next recursive call of this, the amount of work done on it, there will be a calls of it, and each one of them will do f of n, but now n will be n over b, right? So I'm making a recursive call on it. You know, as we had before, we have our main like instance of the call, and then does some number of splits, a of them, and each one of them has n over b. And now we're saying instead of this being whatever this is to some power c, it's now going to be some function of that. So the amount of work done by this block will be f of n over b, and there will be a of them. So the amount of work done on this layer in total will be a times f of n over b. Does that make sense? Now, if I have that in one of these layers, because I also said that f of n is monotonic, this follows, in case anyone has any issues with the numbers here. What I can do is I can just say in one single layer, does it get bigger? Is this layer bigger than this layer? So all I need to see is whether or not, so if I had that f of n, for example, is bigger than a times f of n over b, then that means that it's shrinking over time. That means every recursive call is going to be smaller than the previous one. Does that make sense? Each recursive layer will be smaller. So we can actually, from this, we can actually get a proper function. We can find at least one function that satisfies, or I'll look at the other case. I'll look at this case to give you maybe a little bit easier math. If I say f of n is equal to a times f of n over b, and we look at this case, right? That's a case where they stay the same every single layer, right? It does the same amount of work every single layer. And we can actually just solve what f of n is in this case. You can use a little bit of intuition. There are actually infinitely many solutions to this, but there is a particular form for these solutions. I'm going to give you one case of it. If you'd like to extrapolate it or look at the slides that I post on Piazza that has this answer, you can look at that. But one answer for this is that f of n is, if f of n is equal to n log ba. Okay? So if it is of that form, then these will be equal. That make sense? So you can just plug it in here and actually show that they are equal. If people need me to do that, I can. But if we do this, right, we'll have n over b to this power. The log ba is going to cancel out. We'll get n to this power over a times a. A's cancel out. We end up with this. So f of n is equal to this, and a times f of n over b is equal to this. Also would be equal to f of n over b times a. Okay, so that's one possible form of it. So we actually have our bounds are going to be when this is equal to this function, or something that is asymptotically bounded by this function. I'll be very precise with this to give you some help. So this is going to be true, in fact, of all things that are asymptotically tightly n to the log ba. So that'll be like a constant factor won't actually affect this. It'll still be equal to each other asymptotically. And then these other cases, right, when we have that this f of n is strictly larger than this, right? So that'll be that f of n is strictly lower bounded by this. Does that make any sense to people? What it means to be strictly lower bounded, by the way, it means that it's lower bounded. You remember our thing here. So in this case, we have, here, let me erase a little bit. So this gives us this case, right? And this, we would have that it is lower bounded, f of n is lower bounded, I'll write it like that. F of n is lower bounded by this. So it's lower bounded, that was our capital omega notation, meant that it is lower bounded by it. Lower bounded by n log ba, and that f of n is not upper bounded by it. So I'll just shorthand for that same function. So this is what it means to be strictly lower bounded, right? So it is not equal to it. It is something that is strictly larger than this function, asymptotically. Does that make sense? And similarly, in our last case, this is less than, we'll have the opposite, where it will be upper bounded but not lower bounded. And those conditions will make up the entirety of our cases for f of n. Okay? This is a slight generalization of the Master's theorem. This is not actually a particularly important point. In general, the Master theorem, it's much more important that you understand what it is conceptually and the fact that there's multiple cases and when you can use it. Rather than knowing the actual values, you will always be able to look them up. But it is important, like if you ever come across an algorithm, you can say, oh, I can do this as divide and conquer, I can do this many splits, they're all this size, I do this much work, and you can right away know what your asymptotic bounds are before you even write the algorithm. It's very helpful for that sort of analysis. If I want to know ahead of time how good my algorithm is, and if I say, oh, how could I improve my algorithm, I can make A lower somehow, for example. And we'll see a good case of that today. Right? Any questions on this? Again, the thing that is actually really important about this is that you understand conceptually what the Master's theorem is, how it applies to recurrences, and how you could use it in practice. The upper half of the quiz is the more important half, honestly. The lower half I think is interesting. Okay, the bonus, by the way, the bonus of the recurrences is a good example of some of the recurrences you might actually come across that you can use the same reasoning and sometimes directly use the Master theorem, but it's not obvious how. There are cases like that. So you might, if you want some practice with that, I'd recommend looking at that one. These are the sorts of recurrences that you might get on like a technical interview where they're trying to get you. It's good to practice them. It's good to practice them. Okay. Any questions? Okay. Well, we're going to talk about two very interesting algorithms today. This is one of my favorite, this is definitely my favorite divide and conquer algorithm. And it does actually have importance in the real world. We'll be talking about what it is and all that in a little bit. But we're going to start with a slightly simpler problem first, also with a pretty interesting conclusion. So I'm going to erase all the Master theorem. Do you have this somewhere in your notes, just in a very simple form? Because you will, honestly, I can tell you almost 100% you'll need to use this on your first exam. So if you want any direct thing that you should have ready to go, Master theorem, you should have that. I'm not sure if I'll give you the Master theorem directly or ask you to recall it by rederiving it. If I do that, you'll get more time for it, by the way. But we'll see. We'll see. It's a good one to know. It's one I will definitely test you on. Okay, so let's talk about a problem that we do a lot in computer science. Adding two numbers, or multiplying two numbers, sorry. Multiplying two numbers. So let's say that I have two numbers, A, I'll go with X actually. X, sorry. X which is just going to be some number, some random number, 1, 2, 3, 4, and y, which is also going to be some random number, 3, 4, 6, 7, sure, whatever, numbers, and then we want to multiply these together. So we'll say that both of these have n digits, or n bits. We can work in any base system we want, by the way, but we'll say n digits. And question for you all, if I want to multiply these together, how much time does that take? How many individual integer multiplications do I need to do? Any guesses? Yeah. Asymptotically, for n digits. N squared. Okay, so this is going to turn out, the naive thing we can do is basically do every single pair of multiplications and do some bit shifting to put them in the right order. By the way, with bit shifting, just an important note for in a minute, bit shifting is going to be constant time no matter how much you're shifting the bits. In memory, all it equates to is us moving a pointer. So it's actually, in actuality, we're going to treat it as always constant time. Okay, just a small thing. This is going to be n digits. This is going to lead to, naively, an order n squared algorithm in the number of individual multiplications we would need to do. We're counting multiplications and additions, is what we care about here. Okay? So maybe we can use divide and conquer here somehow. Anyone got any ideas? Okay. Well, first, let's figure out some way we could divide the problem. Okay? How about this? How about I separate each of mine into a first half and a second half? Okay? Now, what would be the what would x, y be equal to? So we have here. I'll label this x left, and I'll call this x right. I'll call this y left. I'll call this y right. Okay? It turns out, I'm just going to make sure I don't mess up the formulation of this, that this is going to be equal to, now, x left bit shifted. So I'm using this notation to be bit shifted. So this is like this many indexes is how much I'm moving it. So I'm bit shifting it m times. That's like digit shifting it. Everyone know what bit shifting is, by the way, before I keep using that word? Can I see thumbs up and thumbs down if you know what bit shifting is and what you don't? If you don't? Okay, I'm going to keep using it. Cool. If we're trying to multiply by 10, we can just multiply it. This is multiplying by 10 to the m. But we can do that very easily. We don't need to do an actual multiplication. Okay, so we have that plus xr, right? So this is pretty obviously this. So this is just equal to x now, right? So this is just the upper half, then multiplied, bit shifted m times, plus the lower half is just going to be x. Multiplied by the upper, multiplied by y, which will say yl, also bit shifted m times, plus yr. This is pretty clearly going to be equal to the same multiplication, right? Because this is just equal to x, this is just equal to y. So same multiplication. Okay, but we can do this out now, and what would we get? I'll again make sure I don't mess up anything on here. It'll be xl, yl times, this is bit shifted 2 times as many, right, because they're both the higher end. I'm also just doing the multiplication out. Then I'm going to get xl yr plus yl xr. This is the cross terms times this, bit shifted m times. And then finally, plus xr yr. Okay? That makes sense? Now, what we notice is this has some number of multiplications in it. All of them are of integers that are half the size. That makes sense? So here, xl is going to be exactly half the number of integers if we're saying that it's some power of 2. It'll be exactly half the integers of the full x, and so will yl of y, if we're saying the same size. Yeah?
Is that the xl while in the beginning? Together or one new?
They're multiplied together. Yeah. No, there's no concatenation here. It's multiplication. Yeah. I'm using the dot sort of as it's a bit shifting thing, but yeah, they're all multiplied. I can remove this if that makes it less confusing. Yeah. So those are just the halves, and they're multiplied together, and it gets you all of this, right? Okay. So now I have all of these, and I'm also going to label each one of these just to make it slightly clear. So I'm going to say that this right here, I'm going to call Z2. I'm going to call this whole term Z1. I'm going to call this term Z0. We'll see why I'm doing that in a little bit, but I'm just going to name them all, so then our full operation is just going to be Z2 times, it's going to be bit shifted, this is going to be bit shifted 1 time, and this is going to be bit shifted 0 times. So that's going to be our new form of it. Now, what I can do is I can sort of recursively call this, and when I want to do this multiplication, I can recursively call my divide and conquer multiplication that I'm doing here, so on and so forth, until I hit a base case where I just multiply two digits together. Okay, so what would be the recurrence of this? I'll let everyone, you should be able to solve this one. Every single person should be able to come up with this answer. Oh, wait until I see people understanding it.
I have a question.
Yeah, question.
How long should we assume that addition takes?
Addition we're going to assume is constant time. Yeah, so each addition, we're counting the total number of multiplications of digits, and if we have, so I guess, fair enough question, I'm going to answer right now. If I have two, let's see why addition and multiplication are slightly different. If I have two long integers, right, if I have my x and my y, 7, when I add them, all I need to do is go at each single one of these places and add them individually, and then carry over at most 1, right?
So it's linear time.
So it's linear time for n long things. Okay, sorry, I'm getting ahead of myself because we're going to be counting the overall number of multiplications and stuff on like digits, which would be constant time, same as multiplications. Fair point. So yeah, so to get the recurrence, we should actually know this, because the amount of work that we're doing to combine them is doing two additions of things that are half the size. Yeah. Okay. Yeah, do you have an answer up there?
Yeah, twice, 2 times t of n by 2 plus.
So close. How many multiplications are we doing? Doing 4 multiplications. Each one of those multiplications we're going to do by a recursive call, right? So this is equal to what?
2 times.
Going to be 4 times. Because I'm recursively calling. Remember, each time I see multiplication, I'm going to be calling my algorithm again. Okay, this is like the form of a recursive algorithm, is I have now halved the size of my problem, and I'm going to call my algorithm again on it. So it's going to be 4, because I have 4 multiplications here, t n over 2, because each one of them is half the size. Each of these integers are n over 2 length. And then to add them, this is where this point matters. We'll also see why it doesn't matter, but this is where this point matters. Doing the addition, when I'm doing addition of things that are size n over 2, they take linear time, which is going to be n time, and I'm doing 2 of them, I'm doing a constant number of them. So this is just going to be plus n. It is actually explicitly n because I'm doing n over 2 plus n over 2. Okay? This makes sense? This makes sense? Okay. So if I solve this recurrence, how much have I improved over my n squared? Everyone, solve this one. You just did the practice. Tell me what this is equal to. I'm gonna let people solve it. Solve this one. Do it. This is good practice. It's an easier one than the ones on the quiz, even. Yeah. 2. It's going to be exactly equal to something. It's going to be tightly bounded by something. Sure, in the back. You're very clearly reading off your phone. Okay.
It's n.
So n log 2 of 4, which is equal to what? What is log 2 of 4? 2. This is n squared. Oh no! We got nothing. So again, this is another case where just blindly applying divide and conquer does not actually give us anything, but unlike the other case, we can do something clever here. So this is going to be the Karatsuba algorithm. And what we're going to try to do is we're going to try to convert this in such a way that our recurrence is going to give us a lower bound. It's going to give us a lower tight bound, I mean. So one option for that, so the two options that would change our bound here, is either we can raise B or we can lower A. Any guesses which one we're going to try to do? I did sort of say it earlier, but I'll let you, yeah?
Lower A.
So we're going to try to lower A, right? So somehow we would like to have fewer than 4 multiplications to do this. And this is going to be why we labeled each one of these. So this just requires a little bit of clever reasoning and math. What we're going to do is we're going to define another z term. Okay, I'm going to erase this now. What we're going to do is we're going to define another term. It's going to be, again, I want to make sure I don't make any mistakes, all right? Z3 is going to be equal to, XL plus XR times YL plus YR. Okay, so this is a different term. This is a totally new term here. This is going to be not equal to x and y, just to make sure there's no bit shifting in L and y, right? Sort of an arbitrary step it might feel like, but we can do a little bit of clever math. So first up, let's FOIL this out. We get XL YL plus I'll do it like this, XL YR plus XR YL plus XR YR. So I just did it all the way out. Cool. And now I'm going to subtract from it. All right, so this is, oh, sorry. I'm doing this a little bit backward. I'll do it an easier way, actually. Do it either way. So I'm going to define this first. This would work, by the way, but I'll do it a slightly simpler way. So first I'm going to take Z1. Okay, first I'm going to take Z1. I'm going to show that we're going to show the relationship between Z1 and Z3 in a second. Z1 is equal to, I have it already over there, but it's going to be XLYR plus YLXR. And what I'm going to do, so I FOILed this out already, so you got a little sneak preview of it. What I'm going to do is I'm going to add all of the missing terms from this, like completing the square type thing. So I'm going to add all the terms. It'll now be XLYR plus YLXR plus YLXL plus YRXR. Okay? And this is clearly not equal to each other at the moment, because I'm just adding terms to it. YRXR. What I'm going to do is I'm going to then subtract the terms I added. This is just to show you a nice clean proof of this. So I'm going to then subtract YLXL plus or also subtract, I'll just write it like that, minus YRXR. Okay? Has this got me anything? Well, yes. I've already shown that this right here is equal to Z3. Okay? So we have Z3. How about these two? Are these anything? Sure, yeah, go ahead.
Z0 and Z2.
They're going to be Z0 and Z0 and Z2. So I can say that in fact, my Z1 is going to be equal to Z3 minus Z2 minus Z0. Okay. What has this got me? Why did I bother doing this? Yeah. Exactly. To find Z3 is only one multiplication and two additions, right? So while these may be, like I have to add them first, they are slightly larger numbers, I'm still only doing one multiplication of them. Okay? So now, if I want to get this entire equation, what I can do is I can plug this in here, right? So I just find Z1, Z2, and Z2, Z0, and Z3. And then my overall thing here is now going to be equal to Z2 bit shifted plus, now this thing is all going to be equal to Z1. So it's going to be Z3 minus Z2 minus Z0 bit shifted m times, and then plus z0. So now my equation here, right, I'm reusing z0 and I'm reusing z2, so I don't need to do those multiplications again. I'll just keep them in memory. Okay? So now how many multiplications am I doing? I'm doing 3 multiplications. I'm doing 1 for z3, 1 for z2, and 1 for z0. I've removed the z1 term. And now what this gives us is a new recurrence. What is that recurrence? Three t. So it's going to be Tn is equal to 3t n over 2 and still linear time. We're doing more additions, but there's still only a linear addition. Okay? And now, what does this come out to? Yeah. And log 2 of 3. Okay? So this is approximately, by the way, I have it written down here, is approximately n, what is it? Oh, I didn't write it down. Anyone have it? Someone, calculator. 1.585. 1.585, thank you. Do that. So we have gained asymptotic speed just by doing a little bit of clever numerical manipulation. It may be tempting to see this problem, see what sort of math is required to do it, and say, oh, you can't do faster than n squared. But it turns out with a little bit of clever numerical manipulation, we can actually do better. Okay? So it turns out that actually in practice, doing it this way rather than doing the other way is actually faster too. Fun fact, by the way, there is faster ways to do it too, and we'll talk about that in a little bit. But this is a pretty interesting thing. I think this should show you a little bit the power of understanding recurrences. I understood that these are sort of my 3 levers, and I can choose and see if any of them are possible. And I can be inspired by the fact that if I were to lower this, I would get a better bound, to be able to look at this and say, oh, I can actually rearrange this so I do fewer multiplications, which is exactly what Karatsuba did. So this is hopefully justifying a little bit why master theorem is so helpful for iterations and for finding these new algorithms. Okay, cool. So now we're going to talk about my favorite of the divide and conquer algorithms, and what I think is the most important algorithm we will have seen in this class thus far, by kind of a wide margin, actually. Okay, so let's start with our problem. So we did integer multiplication. Now we're going to do matrix multiplication. Okay, so if you're unfamiliar with matrix multiplication because the linear algebra class UMass isn't great, then here is what it is. We have 2 matrices, which are 2-dimensional arrays with some number of terms. We can say they are any sort of real value numbers. Cool. We'll call this one A. We'll call this one B. And to get the matrix multiplication of these 2 things, there are actually 2 equivalent ways that we can describe this. I'll talk about I'll do first the one that is most commonly covered in something like 235, which is if I take all of the rows of A, each of the rows of A, etc., and I take all of the columns of B, call this B1, call this B2, etc., then I can say that the matrix multiplication of this is just going to be every one of these each one of these columns multiplied by one of these rows. Okay, so that is each one of the terms in my resulting matrix is going to be, like, the first term here is going to be A1. It's going to be dot producted with B1, which is I'm going to sum the multiplication of each one of the elements. So I'm going to multiply this element by this element, and I'm going to do that for each one of the elements, and then I'm going to sum them together. I'm assuming a little bit of a linear algebra background. If you really don't understand this, it's not tremendously important for the algorithm, but I recommend that you review linear algebra because it's important in general. So this will be A1, B1. I'll write it like that. That's a dot product. Don't need to worry about it too much. Anyway, so each one of these terms, the ijth element is going to be ai, bj. Okay? So now, specifically, how many multiplications do I need to do? So now we're not worrying about how big the multiplications are, but just how many multiplications do I need to do? I'm going to wait for some new hands. I'm getting the same crew every time. So everyone think about this. Think about this. So every single one of these elements, right, is going to be some dot product of these. That is, if I have A1, B1, just to give you a different format, this is going to be, or I'll say like this. If I have two arbitrary ones, let's make them C and D, let's say, then it's going to be the sum of, if these are both vectors, sorry to change notation on that a little bit, this will be the first, or the ith element of that one times the ith element of this one, and then they're going to be multiplied together and then summed up totally. And that's going to be what it is. So each one of these elements of this is going to be multiplied. That helps you count your multiplications. So then, how many multiplications go into a single one of these terms? How many multiplications does it take? These are n by n matrices. Sorry if I didn't say that explicitly. N by n. They're both n by n. Yeah. So we're going to be multiplying each of the elements in this column with each of the elements in this row. Okay? So that's going to be, yeah, Sonny? Is that m times n? So what is m? So it's, so each of them are going to be n long, right? So I'm going to have an n long column, an n long row here, and I'm going to multiply each of the elements together, right? So I'm going to only do n multiplications. So each one of these is just going to be n multiplications. I'm counting in terms of multiplications, by the way, now, not in terms of like bit operations or anything like that. So each one of these is going to be order n, and how many of them do I have? I don't. The resulting, how many of these do I have? How many possible combinations of rows and columns do I have? N squared, n squared. So there's going to be every possible combination of these columns and these rows. So there's going to be n squared of them, meaning that the total number of operations I need to do, total number of multiplications, is going to be n cubed. Okay? Now, that's a pretty big asymptotic bound. Can anyone tell me why I care about matrix multiplying? Right there. Computer graphics. If I ray tracing, by the way, all matrix multiplications. Anything else? There and down. Sure. Linear regression will be a single matrix multiplication. Would be cool if we knew it fast, but that's not necessarily going to be our bottleneck. Anyone else? Transformers go on the far other end. Yes, absolutely. I'll say in general, machine learning, neural networks, AI, runs on linear algebra. We are going to be doing matrix multiplications of enormous matrices. If you hear about some 1.5 trillion parameter model, those numbers are being matrix multiplied. So we actually care quite a lot about this asymptotic bound. This is we're talking about much larger numbers than we normally talk about with computer science. Yeah?
What is the n cubed?
That is the number of multiplications, like individual multiplications, like integer or number multiplications that are required to do a full matrix multiplication of an n by n times an n by n matrix. Okay. This was meant mostly as a refresher for linear algebra a little bit so you can understand the impact of this. But linear algebra is really everywhere in computer science, actually. It is fundamentally very important. By the way, as a side note, if you did not recall this, and you are into machine learning, read a linear algebra textbook or something. Watch 3 Blue 1 Brown, actually. He has great videos on that. But it's an important thing to know. It really is. Anyway. So matrix multiplication is both an incredibly important and ubiquitous operation that we need to do, and it is also done with a very large scale, meaning that we care about our asymptotics quite a lot. So if there is any way that we can improve this n cubed bound, we would love to do it. Okay? Now we're going to start with an idea. Let's see if we can do divide and conquer. We love divide and conquer. Let's see if we can do anything with it. Anyone have any ideas? I'll allow any hands for this one. Yeah, what's up? Sure, let's try it. Let's try it. So, turns out that if I split these into quadrants, so let's divide them up like this. I'll say that A is going to be split into, I'll say this is A11, A12, A21, and A22. Okay? I'm going to be multiplying that by my B matrix, which is now going to be B11, B12, etc. Okay? Well, it turns out that, in fact, we can do this just by quadrants. So we can rewrite our matrix multiplication. Anyone know what the top left element is going to be? Yeah. Or top left quadrant, actually, because these are going to be larger than just numbers. Yeah? So it'll be A11, so not quite, by the way. It'll be A11, B11, plus A12, B21. This is like this column multiplied by this row, if that helps you understand it. Question?
So you just treat it like it's normal matrix multiplication?
Yeah, it does actually work. So this is a property of linear operations. Basically, it will scale like this. So it does actually work like this. And interestingly, we can do all of these. So I'll do, I guess I'll do them all. It's A21, B11, plus A22, B12. Then it will be A11, B12, plus A12, B22. This last one is also two multiplications, and they're added together. Okay, you can fill it in if you'd like. So now we've done this, we can recursively call on each one of these if we'd like to. What would our recurrence be? All this t of n equals what? I'm counting the number of multiplications. So it'll be 8t, right? Each of these is one of these multiplications. Okay? And I have them of what size? Yeah. So it will not actually be n divided by 4 because I've had n as the length of the they're an n by n matrix. Yep. So not quite. It'll be n by 2. So each one of these are a square matrix with n over 2 length. The whole number of elements is going to be 1/4 the number of elements, but the n will be only halved. Okay. Okay. And how much work do I do on each one of these? Not quite. So it is in fact going to be n squared. Can anyone tell me why? And the one who said it?
No.
Yeah, can you tell me why?
Not really.
Okay. What is the other thing I'm doing besides these matrix multiplications? The only other thing I'm doing? I'm adding. And how big is this? So it's going to be n over 2 by n over 2, which is order n squared elements. And I'm going to be adding it to something else that is order n squared elements. The number of additions I need to do is n squared. That make sense? Okay, everyone happy with that? Okay, so now this is what? We get to use master theorem again. What is it? Nice. It's going to be n to the power of log 2 8, which is going to be n cubed. We got nothing once again. Oh no. Well, Strassen, this is his algorithm by the way, took a note out of Karatsuba's book and said, what if we can change these numbers? Anyone want to make a guess which one of these numbers we're going to change? We're going to change the 8. How are we going to change it? We're going to make it lower. So, how do we do that? Well, I'm actually going to go through the algorithm. The algorithm is somewhat numerically involved, by the way, but I'm going to do it because I want to show you what goes into this, and we'll talk about a little bit after that some extensions. So, what he does, Strassen realizes, is that we can create some intermediate terms. So this is still going to be we're still going to be splitting it like this. And we're going to create intermediate terms. And I'm going to just write them out. If you want to take some notes or something, now's a good time. It's going to take me a little bit of time to write this out. So we have M1 is equal to A11 times B11. We have M2 is equal to A12 times B21. We have M3 is equal to A1 by B22 minus B11. M4 is equal to A22 by B22. And M5 is equal to A21 plus A22 times B21 plus B22. M6 is equal to A22 minus A12 by B22 minus B12. And M7 is equal to A22 minus A11 times B12. Okay, cool. So, a little bit more numerically involved, but we now have these things. And how many multiplications are done here? Only 7. There's only 7 matrix multiplications actually done here. We have some additional subtractions and stuff. It's going to each one of these will be n squared, but only n squared, and there will only be a constant number of them. And then we realize that the output here, we can actually rewrite our matrix multiplication output to be M1 plus M2, and we're not done yet, M5 minus M7, M3 plus M6, and finally M5 plus M6 minus M2 minus M4. Okay, lovely, lovely. So each one of these, by the way, is going to be an n over 2 by n over 2 matrix, each one of these things. So this is going to be quadrants. So we're going to place them in each of these quadrants appropriately. Now, what is the recurrence of this, of doing this whole operation? T of n equals what? 7t n over 2 plus how much? Still only order n squared. Where again, this is implicitly I'm doing order n squared. It is some number of n squares. So each one of these multiplications and additions are going to be n squared. It'll be some constant number of them. They'll all be n squared over 2. Okay. And this is what? What is our bound now? I heard it sort of trail off there. N to the power of log base 2 of 7, which, human calculator? It's going to be 2.8, yeah. It's 2.8074. And 2.8074. Now, we have improved it. This is another one where, naively, you might look at matrix multiplication and say, there's no way you can do better than n cubed. It's just impossible. It turns out you can. and this isn't the end of it. I'll talk briefly. Let me see how much time. I'll go on some tangents here if we have time. Okay, we don't have that much time. Small tangents then. Very recently, Google DeepMind actually released a paper where they did this only for larger matrices, but they subdivided it into, I believe, 116 different terms like this, and then you can reconstruct it, and it actually beat this bound, which has been standing for quite a long time. This is a state-of-the-art bound, by the way. This is one of the few very, this is what we do. This is actually, if you were to go into NumPy and do matrix multiplication, you're doing this. You are actually doing this under the hood. You're not doing something else. Although there are different algorithms if we know that they're sparse, that is, there's a lot of zeros in them. There also is, another slight tangent here, there are ways that we can approximate matrix multiplication, and one of the most interesting results I found in any of the algorithms classes I've taken is that we can actually do matrix multiplication in order n squared with arbitrarily little error. So that obviously actual runtime will grow, but asymptotically it's still n squared, and that is for epsilon goes to 0 error. Very, very, very small error in our algorithm. And that is through randomized matrix multiplication. So we will randomly select columns and rows to multiply together. I think if you're interested in this, if you'd like to hear the actual algorithm, firstly you can look up its importance sampled randomized weight matrix multiplication if you want to look it up. Also, I can talk about it in office hours. I think it's a very interesting algorithm. But the fact that we can have arbitrarily small error is also very cool. Another thing that can be done in practice. We do lots of matrix multiplication is a very, very optimized field. It's something that you can see very, very interesting algorithms for that get really good bounds. Anyway, funny little aside also, Strassen, the originator of this algorithm, also actually has a better integer multiplication algorithm than the one that we learned. So he took inspiration from Karatsuba, created this algorithm, and then went back and beat Karatsuba, and actually gets it's approaching n log n. It's very close. It's like n log n plus n log n or something like that. It's very close to n log n. It's a cool algorithm, but it's not a good example of divide and conquer, so we won't talk about it right now. Yeah. Okay. I guess one final extension I want to make with Strassen's is what big assumption am I making here? I'm making a recursive caller. I'm making a big assumption. One that is almost always going to be wrong in practice. Yeah.
You have a 2 by 2.
So I have a matrix. Firstly, they're n by n by n by n, which is a whole thing. But secondly, I'm assuming that they're powers of 2. I'm saying that I can subdivide them evenly each time. What do I do if they're not? How could I use this algorithm, or do I just have to find a different algorithm? Yeah. So we in fact can fill with zeros. So the real runtime of this is actually going to be this plus a little bit, plus O of 1. So it's going to be plus a little bit. This is going to be essentially we have to round up to the nearest power of 2, and then we do the algorithm. So it'll be slightly more. It's not going to be substantially more in practice, like actual runtime, especially since in reality a lot of these algorithms are super parallelized. But it will be a little bit more than that. But this will be 0 when n is a power of 2. Okay? So small little detail there that I think is interesting. Maybe I'll have you guys implement Strassen's as a bonus or something. By the way, so last bits is going to be announcements here. Homework has been released, and here's how it's going to work. So the assignment is it's a project. It is a single project. You're going to be generating mazes, perfect mazes, that have a single solution, and you're going to use this using a divide and conquer algorithm. You're going to analyze it, and you're going to get to generate these mazes. We have visualization already for you, so you just need to do it on the algorithmic side. And the timeline for this is that there's a written portion due next Wednesday at midnight. And then after that, you'll have a week to code it and get it to work and fix your written part if you get anything wrong with the written part. Okay? So that's the timeline on that. This is, by the way, a difficult assignment. So just so you know, I recommend that you start on it early. I am estimating that in actual hours, it will probably take in the range of 6 to 15 hours, depending on how comfortable you are with the topic. So plan accordingly. I just do spend some time on it. If you chip away at it, it won't be that bad, but I recommend that you don't save it all for the last minute, because it may not be possible for some of you at least. Lastly, by the way, last thing, office hours have now been announced on Piazza. So we have the office hours there, I think all of them besides UCA's. And also the SI session is when?
Tuesday, Thursdays at 7 p.m.
Tuesday, Thursday, 7 p.m. Where?
Du Bois, 1201. It's on
1201. It's on Piazza also. Cool. All right. You're free to go. Goodbye. Don't forget to scan your quizzes. I'm getting too many emails about uploading quizzes for people. Please. Thank you. Yeah.
I was confused at the very beginning, like how you got N over 2 and it just kept coming up.
Oh,
So I was just like,
and that's in multiplying?
yeah, this is from the beginning.
So splitting my numbers, that's x left,
Right.
x right.
Yeah.
Each of these, so this is n digits, right?
Oh, that's represents the subproblem.
So it's the size of the subproblems. Yeah. So I'm recursively calling on smaller subproblems.
And that was the same thing for like how you just
Exactly. So each of these is half the size. That's half the length.
And then A, like 8, is that like the original? Like what you do?
So it's the number of cases multiplications. So it's not on your own, it's all of the multiplications that have to be.
Oh, right, okay.
It's the number of times I'm calling a multiplication. Yeah. How does one find that? In the case of DeepMind, they used AI. In the case of Strassen, clever math. Basically, almost anytime. So you can think of it as a system of linear equations. And if I have 7 of them, then I can solve for the 8th one. And that's sort of just a rule. So anytime I have a system like this, I can always figure out the last one without directly calculating it. Yeah. That's like I'm sure that's like a theorem or something. So he knew that it existed, and then finding it was a matter of elbow grease, probably. Yeah. If you work out these, it might become more obvious, by the way. These aren't arbitrary. I mean, you can look at what they are. Like, lots of them are very similar to each other in like structure. Yeah. It's a lot to write them all out at once, but they conceptually are more simple than they look. Yeah. Anything else? Thank you. Yeah. Yes.